Good afternoon, everybody. My name is Matthew Tenhuko, and this is my Physics Lab 6 report on magnetic molasses. So the purpose of this lab is to go over Faraday's law relating time-varying magnetic field to a curly electric field. Whose path integral around a closed path is not zero, but provides an EMF that can drive the current. So basically what we're going to be doing is looking at how an induced current from a magnet can produce a magnetic force that slows down the magnet if this magnet is dropped through a conductor, such as a tube made of foil, which is what we use. We need to collect observational data and model the magnet-tube interaction computationally so we can compare both the data physically and computational and see if our predictions are correct. Fundamental physics principles include magnetic field equation, magnetic moment, magnetometer, the system being the bar magnet, and surrounding me everything else, possible external magnets, and also like the foil tube. And fundamental, also, we have to look at Biot-Savart's law, magnetic flux, Faraday's law, and Ohm's law as well, relating to Faraday's law. There are the equations for each of them. So materials used are including smartphones for our magnetometer, a bar magnet, relatively 4.8 grams, which will be important for calculating how fast it should fall when not in a foil tube, a roll of aluminum foil the tube will use for the experiment, and a meter stick or ruler measuring the dimensions of the tube. First, so for the experiment, first we have to mark the north part of the pole as seen in the diagram, and we also have to use the magnetometer to find this north pole, seen on the left. From there, we have to hold the tool vertically, position magnet just above it, and then we have a smartphone ready to record everything, and once we dropped it, we'd record and wait until it fell through the tube, and then we'd go back in the video, check when it started to fall and when it fell through the tube, and record that time data. So the data we got is here. We did 5 trials, and the predicted time with the known weight is 0.047 seconds, which is really quick. But the average actual time was around 1.516 seconds, meaning the foil tube actually provided a lot of resistance, but meaning it provided a much stronger magnetic force and a strong induced current. So the code we use to model this starts off with some variables and the graph we need to make, followed by creating the tube of aluminum, which we'll see later. After that, we have to just create the tube and then look at its range, as well as creating the bar magnet. We have initial conditions for the bar magnet as well as the tube, going for their magnetic fields, calculating magnetic flux, and showing now this is the part where we make the simulation happen when letting the thing drop through the conductor, and a bit more flux calculations and even more calculations for the force of the magnet and printing everything out in the end. So this is what we got for the code, the demonstration, and this is the graph we got. So calculations was 1.065, which is relatively what we got to. So we know experimentally we did this correctly. So what if the resistivity of the conductor were reduced to 0? Well, this would mean the magnet would actually just not fall at all, or at least fall even slower than before. So because 0 resistance would mean the induced current would produce a magnetic field force equivalent to the field of magnet, because no resistance is reducing the induced current. This is why magnets can levitate above superconductors, as they lose all resistance at very low temperatures. And what if holes and slots were cut in the tube? Well, that would just result in the induced current not even forming, being that the tubes are not connected, meaning that it's not a connected circuit. This would mean that the magnet would just basically fall through the tube, as if the tube didn't exist. It would fall like it was falling outside of the tube. And some sources of error the magnet we used was a bit broken, which could affect its time, as well as the tube wasn't a perfect tube. The magnet could have been sliding on the foil. So you took that into consideration. Thank you.